So let's hear the next speaker, Rachel Hong.
Thank you. Hi, everyone. I'm Rachel. I am a PhD student at the University of Washington, and today I'll be talking about web scrape data sets and how data collection practices can introduce their own forms of biases. So as a content warning, this talk will include discussion of inappropriate content and problematic stereotypes, and I should have some time at the end for questions. Cool. So as you all may be familiar with, over the last decade, image data sets have been growing in size in order to build larger and more effective machine learning models. So what this means is to keep up with these increases in magnitude, more and more data is coming from the internet. With this scale, though, comes certain problems, as it no longer becomes feasible to manually check each individual sample, as ingesting data from the internet often requires methods to sort through irrelevant or potentially harmful and inappropriate content in order to output these final curated data sets. So we're also just starting to see recent trends in which web scrape data sets are relying on automatic filtering methods. So if we take a step back and we look at the traditional machine learning pipeline as shown here, this kind of initial data collection step is actually split into two for web scraped machine learning, where there's this kind of hidden data cleaning stage, which relies on these existing, already trained models in order to remove unwanted data. And so in our work, we're focusing on this specific step here of data cleaning to understand what kinds of data is being discarded when we're relying on existing models that might have their own biases or inaccuracies. And we're also trying to understand if these filters are actually successful in keeping out undesirable data. So here's some motivating example from prior work on image text data sets. And so image text, for some background, one sample consists of an image and a corresponding caption that is taken from the web. So the common data filtering technique uses this existing quality filter model that is essentially tasked with the question of assessing if the caption accurately describes the image. So if the model answers yes, then it's kept in the data set, otherwise it's discarded. So say we have two examples. They both share the same image of astronaut Eileen Collins, and say we have one with the caption of an astronaut and the other with a caption of a smiling housewife. So according to the parameters and biases of this model, prior work shows that the first example actually would have been discarded, and the second problematic one would have been kept in the final data set. So this gives some intuition as to how these biases can be introduced in the filtering step, but this is actually a hypothetical example. It doesn't exist in any data set, to our knowledge. And so what our work is trying to understand is if this kind of discriminatory filtering actually occurs at scale. So going forward, I won't be giving any cool examples, unfortunately, but it'll be more about trends that are across a data set. So for the rest of this talk, I'll be presenting our audit of the filtering stage of a large web scraped image text data set. And I will first go into some background of the machine learning pipeline that relies on this external model, and also present our findings of our large-scale empirical analysis. So we find instances of bias where, for example, text written in non-Western languages is more likely to be excluded than text in Western languages. Finally, I'll conclude with some discussion and recommendations based on our findings on data filtering practices more broadly. So the main takeaway that I hope you come away with today is that issues can arise in the hidden steps of data cleaning, which compounds existing issues of web scrape data sets for training large models. And so what this means is that auditing the filtering stage is actually incredibly important because contents in the final data set won't reveal what's already been discarded. Okay, so for some background, we decided to focus on the DataComp common pool data set. So this consists of 12.8 billion image text samples taken from the web, and to my knowledge is currently the largest publicly available image text data set out there. And so we focus on this data set because it's also the follow-up to the popular LION data sets, of which LION 5B last December was actually recently taken down due to the presence of CSAM, or child sexual abuse material. And so to understand how content like CSAM can end up in the data set, we need to understand how exactly these data sets were sourced and for what purposes. So this is a kind of a pipeline of both DataComp and the LION data sets. So first, for the data collection stage, all the samples are sourced from Common Crawl, which is this archive that provides a large snapshot of the web. For the data filtering, or the data cleaning stage, there's a series of filtering steps. So first, duplicates are removed, and then DataComp actually applies an NSFW, or not safe for work filter, in order to kind of avoid the presence of CSAM that had been found in LION 5B. So this outputs what the researchers call common pool. This next step is what both DataComp and LION do, and they claim that this is kind of the essence of why their data set works so well. So it's called clip filtering, and what it does, it relies on this already trained OpenAI clip model that maps images and text to the same representation space in order to answer the earlier question from the motivating example of if the text accurately describes the image. And so this outputs to what we call the filtered data set. And so the next stage is the pre-training stage, in which the researchers then train their own open source version of a clip model, which again maps text and image to the same representation space using contrastive learning. Then the final stage is fine-tuning, or kind of looking at downstream tasks. I won't go too much into detail, but there's a lot of work on how clip models are really good for these other specific tasks. Okay, so I want to highlight this clip filtering step here, since at first glance, it already seems very odd that we're using a trained clip model to filter data to train another clip model. And so in fact, according to OpenAI, clip is not intended for filtering. So their model card states that any deployed use case of the model, whether commercial or not, is currently out of scope. This is with good reason, as there's a lot of prior works that show that OpenAI clip embeds racist and sexist stereotypes. Despite all of this, popular generative text-to-image models like Stable Diffusion, Midjourney, and Google's Imagen all train on subsets of LION 5B, which is obtained through clip filtering. And because Stable Diffusion and Midjourney each have over 10 million users, we can see that data filtering practices do have wide reach, but the implications are very unclear. So if we look again at this clip filtering step, it's very reasonable that the harms and biases of clip are kind of being injected into the filtering decision. And so that's what we're trying to look here, is to assess if clip filtering actually impacts the outputs in comparison to the inputs of Common Pool. So in our study, we replicate the clip filter on the Common Pool small-scale version of the data set, which has 12.8 million samples. And we group these samples according to modality. So we use a variety of annotation techniques, like for text, we use the presence of identity keywords. For image, we use an external attribute predictor. And then for source URL, we group by country domain, for example. So to measure filtering bias, we examine differences in pass rate, or the proportion of Common Pool passing the clip filter when broken down by group attribute. So for example, a group that has a pass rate of 0.5 means that 50% of the data from that group are passing the filter. Again, with all group fairness metrics, there are certain limitations, these also just output a final metric, but we do believe that pass rates allow us to kind of make these comparisons at scale. I'll also note here that our analyses are not causal, but rather what's going on in the data set, since it's very plausible that data relating to certain groups might have different website or writing styles or come from different websites. Regardless, we still think it's important to understand what's going on in the data set, given its wide usage. So here's a summary of our findings. First, we find that clip filtering disproportionately excludes data relating to women, LGBTQ+ identities, and non-Western regions. We also find that certain gender stereotypes are more likely to pass the clip filter in comparison to the stereotypes paired with a different gender. Second, we demonstrate this instance of bias that we call exclusion amplification, where groups that are already underrepresented on the web, for instance, before filtering, are subsequently filtered out at higher rates. Third, we find that certain types of copyrighted content, like stock photo platforms, as well as education curriculum platforms, are considered higher quality by the filter, which has certain copyright implications because on these platforms, the images themselves are the assets that are sold as a part of their business model. Finally, we find the inclusion of inappropriate content, and as we estimate that 6 million sexually explicit text samples and about 129 million images from NSFW or not safe for work sites are present in Common Pool despite the use of an NSFW filter. So for the sake of time, I'm going to be looking at this second finding, but please read the paper, and I'm happy to take questions after too. So for exclusion amplification, we first look at images. We pass the images through Amazon Recognition's gender and age model in order to obtain these sorts of like group predictions of age and gender. Although recognition has been shown to have its own biases and inaccuracies, we initially use these annotations as a weak signal for filter discrepancies, and we also validate with other techniques in our paper. So in this graph on the right, we look at images that contain a single detected face that is predicted by recognition to be female. Note here we're using the recognition labels of female and male, even though they typically refer to sex rather than gender. So this bar graph, each bar represents a different age group, and then we plot the frequency when split by whether it is kept by the clip filter in blue or excluded in orange. And so that number on top of each of the bars refers to the total number of samples in that group before filtering. We do the same, the parentheses below show the pass rates, or the proportion passing the clip filter for that group. We do the same thing, but for the male detected group in this figure below. So the main finding here is that groups with fewer overall samples are associated with lower pass rates. So I'll kind of show you what that looks like. So if we look at the older group first, we see that there are fewer overall images from the female detected group, as well as a lower pass rate in parentheses. Now this direction actually switches for the younger group, in which there are fewer overall images from the male detected group before filtering, and then the pass rate is also lower as well. So what this means is that these groups that are initially lower and less represented on the web are actually being kind of excluded at higher rates. So this actually worsens representation disparities in the final training data set, which can compound performance disparities of any downstream task as well. So given the limitations of recognition, and also we were limited by the number of API calls, we also wanted to look at exclusion amplification in the case of text. So we apply a language detection model to all of the text samples of Common Pool. And so this plot here, every single point represents a language. And so the x-axis represents how often, like how many samples this language appears before filtering, and then the y-axis plots the pass rate, or the proportion passing the clip filter. So we find a statistically significant positive relationship here. And so what that means is that the less frequent a language is before filtering, then actually it's associated with a lower pass rate, which means that it's being excluded at higher rates. And so more specifically, if we look at English, we see it's on the upper right. It is the most frequent, and it also has the highest pass rate. And then the Western languages are then on the upper right as well. So this actually is to be expected, because we do know that OpenAI Clip, while we don't have access to the training data set, it is trained only on English text, and Western languages may be more similar to English. Regardless, though, this complicates the contribution of the Lion2B multi-data set, in which its creators tout this data set as being multilingual and diverse and representative, but we now know this isn't the case because Western languages are actually being upsampled more. And so we also know that the web itself is not going to be a representative makeup of language distribution of the world, but this filtering actually compounds that further. So what's interesting to note here, though, is that even though we don't have access to the training data set, because it was trained only on English, we're kind of seeing this trend where this filtering is actually, this filter model is replicating its own training data set, which is something that we're hoping to measure in future work as well. So here again is a summary of our takeaways. We find instances of demographic and regional bias, a phenomenon we call exclusion amplification, the upweighting of certain copyrighted content, and the inclusion of inappropriate content despite an NSFW filter. So all these findings go to show that this existing filtering practice fails to consider societal or legal implications. So now to understand how these issues may have come up, we want to dive into the assumptions behind clip filtering. So according to prior works, OpenAI Clip is intended to be a proxy for image text alignment in order to assess this idea of quality. Yet the notion of quality is undefined in prior work and is often treated as an inherent component of the data, as if something that's high quality it has to be searched for or somehow surfaced. So what this means is that it somehow implies that data filtering is neutral in prior works in order for data curators to kind of avoid responsibility of the decisions they're making when curating data sets. Finally, we see that clip filtering is justified because downstream models achieve high performance on a pre-selected suite of tasks. Yet these tasks are often Western-centric and are still somehow treated as overall progress, as noted in prior work. And at the same time, these tasks ignore societally relevant objectives like fairness or toxicity. So I'll end with some recommendations based on our findings. First, provide justification of data filters. So by definition, filtering will always encode ideology as to what data is considered good or considered bad. Second, report and evaluate data filters. So our work reflects the importance of continued audits, especially for industry practices that are often closed off from the public. Third, account for the prevention and detection of problematic content, as our work shows that the inclusion of NSFW content despite the use of an NSFW filter reveals that automatic filtering might never guarantee the complete removal of things like CSAM. And US laws are pretty strict about that, where one sample in a data set is enough to take the entire data set down. And so this is definitely an area for further research, but this may not ever be adequately addressed at web scale. So that concludes my talk. Here is a QR code. I'm happy to take any questions.
Do you have any questions from the audience for Rachel?
Hi, nice talk. I wanted to ask you about Thai language and Arabic, because they seem to be symmetric in the graph that you showed before. And what is the intuition behind it? Please, thank you.
That's a good question. So yeah, I think in terms of the language, we're really not sure what's going on, just because this filter wasn't intended to be used on non-English languages because it was only trained on English text. So I think that's also the confusing part, that even the prior DataComp researchers were surprised to see that other languages are actually passing the filter. So yeah, so I think that definitely warrants further research. I'm sorry I can't really give other intuition about that.
You have time for another question? I saw someone else.
So since automated methods cannot really capture all the inappropriate content, how did you find how many inappropriate texts were in your dataset?
Also a good question that I can not get into because of time. So what we did is we categorized the websites using the Cloudflare API. So it already provides categories of the websites. And so we found that, and at the NSFW category, I think made up 1% of Common Pool, which was kind of significant. And when we looked at the websites, most of them were coming from pornographic sites. And so we didn't exactly audit the NSFW filter, but we looked at what was in Common Pool. And yeah, so there's a lot of big questions here, because also toxicity or hate speech classifiers, as I think noted in Rebecca's first talk, can also be biased and also classify things differently. But yeah, so this was something that the prior researchers actually didn't do. They applied an NSFW filter, but they didn't even think to look at the websites they were coming from. So we worked with them, and they are planning to do that for the next version, supposedly, yes.
Okay, thanks, Rachel. Can we give another round of applause for the speaker?